Hello everyone, welcome back to my YouTube channel. This is Sahana LK from 5th Sem Tejas section. Today I'm here to discuss about the subject of digital signal processing. I chosen a topic of analysis of the convolution and its importance in DSP. Let us go through the introduction of convolution. Convolution is a mathematical operations that combines two functions to produce a third function. It is widely used in various fields, particularly in digital signal processing. Understanding the convolution is essential for analyzing linear time invariant systems. Let us discuss about the mathematical definition of convolution, where f cross of g into of t, which is defined for integration minus infinity to plus infinity, f of tau into g into t minus tau into d tau. The convolution of two continuous functions is defined by an integral equations. For discrete signals, the convolution is expressed as the sum of overall products of the signals. Mathematically, it is represented as here we're having an equation. To convolve a kernel with an input signal, flip the signal, move the desired time, and accumulate every interactions with the kernel. Here we're having a discrete convolution formula. The discrete convolution of two sequences x of n and h of n is given by y of n is equals to sum of k equals to minus infinity to plus infinity x of k into h of n minus k. This formula illustrates how each sample of the output is influenced by all the samples of the input. They highlights the relationship between the input signal and the filter or impulse responses. Let us discuss about the properties of convolution. Convolution has several important properties including commutative and associative. The distributive property allows for the breaking down of problems into simpler components. Understanding these properties aids in simplifying complex signal processing tasks. Here we can see where x of n is the input, which is undergo the convolution with respect to h of n, we will get our output as y of n. As well as same, h of n is the input, y of n is the what we are getting a desired output. Convolution in time domain. In the time domain, convolution is used to analyze the output of linear systems. It allows us to predict the response of a system to any arbitrary input signal. This analysis is crucial for system design and performance evaluation in DSP. Here we having an example. X of t is defined for 1 and 0, 0 for otherwise, 1 is defined for 2 less than or equal to t, which is less than or equal to 3. Convolution in frequency domain. Convolution in a time domain corresponds to multiplication in the frequency domain. This relationship is captured by the convolution theorem, which simplifies processing tasks by transforming signals using Fourier transformers. Complex convolutions can be commutated more efficiently. Here we having the inverse Fourier transformer f of u, which is equals to f of x minus infinity to plus infinity f of u into e to the power of j 2 pi u x into du, where we having a forward Fourier transformer, which is f of u is equals to minus infinity to plus infinity f of x into e to the power of minus j 2 pi ux into du, where we can see the difference in between inverse Fourier transformer as well as forward Fourier transformer. We're having some other equation. You can go through that. Let us discuss about the applications in signal processing. Convolution is fundamental in filtering applications such as noise reduction as well as signal enhancement. It is used in image processing for effects like blurring, sharpening, and edging detections. Convolution neural network, which is called as CNNs, leverage this concept for future extractions in deep learning, where we can see the graph variations with respect to signal in volt as well as time in second. Let us discuss about the real-time signal processing. Why use real-time processing? Real-time method, which includes data is collected, analyzed, and processed all in one location as well as on one machine. Where signal is given, which will undergo the real-time signal process, we will get a refined data. In real-time systems, efficient convolution algorithms are crucial for performance, as well as optimized algorithms like faster Fourier transformer, which is called as FFT, reduced computational burden significantly. Understanding the implementation of convolution helps in designing responsible for DSP systems. Convolution with finite impulse response, which is called as FIR filters. These filters utilizes convolutions to process signals with a finite number of coefficients. They provide a stable and reliable way to filter signals without feedback. FIR filters are commonly employed in applications like audio processing and telecommunications. Convolutions with finite impulse response, which is called as IIR filters. These filters use feedback to achieve sharper frequency responses with fewer coefficients. They involve convolutions of the input signals with both past input as well as output values. Understanding IIR filters is vital for applications where memory efficiency is critical. Convolution and system stability. The stability of the system can be analyzed using the properties of convolution. Analyzing the system's impulse response through convolution helps identify potential issues. This stability is a key requirement for the reliable signal processing in real-time applications, where delta of t, which is undergoes LTI system, we will get a h of t, where we have equations y of t is equals to minus infinity to t integral x of tau into d tau, where h of t is fixed as well as under the LT, h of s is also fixed. Y of s is equals to x of s divided by s, where y of s divided by x of is equals to 1 by of s, which is equals to h of s. Numerical implementation of convolution. Efficient numerical techniques are necessary for implementing convolution in practices. Techniques such as overlap, add, and overlap save are used to handle long signals. Understand these methods enhances the stability to work with large database sets in DSP. Challenges in convolutions. Convolutions can be computationally intensive, especially with long signals or filters. Managing latency and processing time is critical in real-time applications. Addressing these challenges requires a strong understanding of algorithms optimizations. There are advanced topics in convolutions, such as separable convolutions are used in multidimensional signals. This uses conventional kernels in machine learning showcase the versatility of convolution. Exploring these topics can lead to evolutions in signal processing methods and applications. Future directions in DSP and convolution. As computational research improve, new algorithms are convolutions and continually being developed. Future DSP applications may include more efficient real-time processing methods leveraging convolutions. Let us go through the conclusion. Convolution is a constants of digital signal processing, influencing numerous applications, as well as a solid grasp of convolution enables engineers to design and analyze effective systems. And also continued research and education in convolution will shape the future of DSP techniques. Here we are having some reference. If you want, you can go through. Thank you.